All right, everyone, we'll go ahead and get started. Welcome back to class for this week. This week we are going to be kind of continuing on in our really kind of like evolution of learning JavaScript, and we're going to be talking about some concepts related to asynchronous programming tonight. So there are a few of you who asked in the first homework assignment, hey, can I fetch data, from this API to get a data set? Or, can I do other things that are interacting with other applications to get data? And in order to do that, you need to understand some of the fundamentals of how asynchronous programming works in JavaScript. And we're going to be talking about those in detail tonight and kind of going over some of the different mechanisms that have been built into JavaScript over the years to help make asynchronous programming a lot easier. So that will be the topic of today's class. Before we get into that, a couple just brief kind of logistical items. So first, homework assignment 1 was due today before class, just submitted through Replit. Damola and I will be working on grading those to get those back to you before the next class period. But if you do have any questions or you're still working to finish that up, please don't hesitate to reach out to us on Ed. Homework assignment 2 will be posted on Thursday this week. It will be due on February 28th, as is indicated in the schedule. So you've got really little bit less than 3 weeks to work on this assignment. So homework 2 is going to be covering basically our initial foray into back-end development. And it will be making use of some of the asynchronous programming concepts that we talk about in today's class. So I'll make a post on Ed once that's on the website, and I'll go over it in much more detail in the following class. But we'll do the same thing. We'll have a mega thread. And you're more than welcome to answer or to ask any questions that you might want for that homework assignment. So last class, we had our first kind of real quiz, quiz number 2. And I want to very briefly go over, kind of some of the answers of that quiz, just so that we can kind of recap some of the concepts that we talked about in our kind of initial introduction to JavaScript. So the first question on the quiz was, given this code snippet below, write code that will log my prop to the console. So can anyone tell us how you would log precisely? So the easy way to do this would be to just say console.log. If you wanted to say, what the prop was, say myprop, and then we go object.baz.myprop. And that would give us the value of myprop. But as was just said too, if you wanted to just iterate through the different properties of this object, you could have done that and then printed out basically the last one, going into the myprop kind of sub-property there. So hopefully this one was pretty straightforward. It's basically just nested properties in an object. And you just access the different values of those properties using the kind of dot notation that you're probably familiar with from other languages. Any questions on this one? Okay, awesome. So question number 2, given the code snippet below, using a template literal, to access the value of the first or the 0th element in this case, print the message population of and log the name of the population of each element. So you're on the right track basically here. And if you're reading ahead in the slides, you can see this as well. But essentially here what you do is you have console.log population of. Remember, you use the backticks to indicate a template literal, as was stated. And then if we want to have a specific kind of variable value that's printed out to the command line here, we can do the $, curly brace notation, and then we just access it like we would any other type of object here. We have the first element in cities, which is city0.name. And then we have the same thing, cities.0.population. So this is kind of one way that, again, these kind of template literals can help to format and print out things, if you wanted to just have like a generic print statement for an object, for example. This is one way that they could be used. So any questions on question number 2? Awesome. So finally, question number 3. What is the output of the code snippet listed below? So the reason that the output of this is 7 and 12, so we are declaring our function makeAdder up here, and this is going to return an anonymous function that we have within the method that is essentially then going to return the addition of x plus y. So we have two kind of functions that we have redefined here that we're calling add5 and add10, which are essentially just passing in the values of 5 and 10 to make adder. So if we console.log add5 and pass in 2, that is going to do exactly as we expect there, and it's going to print out 7. And if we do add 10 to 2, again, it's going to do kind of exactly what we expect there and have this print out the value of 12. So basically, what this is doing here is this make adder function is essentially like a pattern that we could refer to in JavaScript called a function factory. So it creates functions that can add a specific value to their argument, and you can then kind of redefine functions based on this. And the reason that this works is that add5 and add10 are both closures. So they are capturing the context of the variables, like we talked about in the last class, that they need in order for them to function properly. So remember the stack frame that we talked about in the last class. It's capturing all that information once they're defined, and then when they're called, it's actually keeping track of all that context and then actually executing things. So that is why it works in this particular example. So any questions on question number 3 from the second quiz? Okay, awesome. So when reviewing kind of the responses that the class had to the quiz questions, I think one of the trickier ones was that last question. I think most people pretty much got the idea of the first couple questions. So I just want to do a really quick review from the last class, going over closures again. So remember, closures are these expressions that work within a specific context. They basically capture or close up a specific context for a function, and they can kind of reuse this context as they're executing in the future. So these contain a function and the state that's needed by that function in order for it to compute something. And you can think of this kind of in this abstract notion of this kind of stack frame or like almost memory being allocated when one of these functions is defined. So really the state here is just referring to the state by this name. But let's take a look at this example again. So here we have a global variable x that we have at the top here. We have a function f. We have a variable y that's defined within that function f. And then we have an anonymous function within the function f that is actually printing out essentially the sum of x plus y and then incrementing y. So if we were to call first set this variable g equal to f, again, this is really just kind of essentially kind of like mapping this function to the variable g. So again, we're calling this function f. So this function f is kind of like executing, but because it's defining another function within it, we're essentially capturing the context that's needed here and assigning it to this variable g. And then when we call g twice, it's actually executing that inner anonymous function. So this inner anonymous function attaches itself to x and y so that it can continue to access them. So if we look at this, this is what you'd consider to be the closure, right? So it's like this inner function needs access to these outer variables, so it's going to wrap those up in the closure so that it has the context it needs to actually execute in practice. So it closes up these references. So if we were to look at this kind of in a step-by-step basis, we have this kind of initial stack frame that gets created. So we call, we basically call the function f here, set that equal to the variable g, and we get this context, right? We have this global variable x. This is already accessible to everything because it's a global variable, so there's nothing really special about kind of capturing the context of that. But this variable y, because it's a part of another function, it is kind of, that's what's really closed up in this reference here within this closure. So we get the context of the variable y here, which the current value is equal to 2, and we get this function definition. So if we move on to the next one, we see that after calling this function, the value of the variable y changes to 3. Variable x stays the same, and this kind of continues on. We get the same thing here. Value of y changes to 4, and so on and so forth. So just keep this concept in mind. These examples with these anonymous functions are admittedly a little bit contrived. It's really just to kind of show you the idea of like how this works in practice. You're probably not going to be declaring like tons of anonymous functions in actual code you write, both because it can be a little bit tricky to understand sometimes, but you will run into this concept, and we will see it later on when we start to talk more about React and some of the concepts there. So just kind of keep this in mind as you're working through the next assignments and as you see examples that we come across in class in the future. So any clarification questions on closures before we move on to asynchronous programming? Okay, awesome. Either everyone understands everything or everybody's very tired tonight. So in today's class, we're going to be going over kind of two parallel topics related to asynchronous programming. So I've kind of broken this down into two parts. So in the first part, which I'm calling Asynchronous Programming I, I'm going to introduce some of the really basic concepts, like from the conceptual level, before we even go looking at code, about what asynchronous programming is and why asynchronous programming in JavaScript is different than in some other languages that you might have encountered. Then in the second half of lecture, we're going to actually start looking at some code examples. And we're going to start to look at some of the mechanisms that we can actually use, some of the language features that have been added to JavaScript in order to reason about asynchronous programming in a way that's a little bit easier. So we'll be basically looking at just using normal asynchronous calls in JavaScript, to using something called a promise, to then using constructs called async and await, which basically help to coordinate some of the different asynchronous calls that you might make in your code. And we'll see why that's important in just a few minutes. So let's jump right into this, kind of introducing some of the general concepts related to asynchronous programming here. So we're going to answer a couple questions here and kind of go into a little bit more detail. So the first is, what is asynchronous programming? Second is, what are threads? And then we'll talk about both kind of why you might want to write asynchronous code and some of the strategies, high-level strategies we can use to actually do that. So what is asynchronous code? So asynchronous code is pretty simply, it allows you to maintain kind of this interactive application while continuing to do some sort of computation. So this computation could be anything from processing data to communicating with different servers or hosts to having a countdown timer that's continuously processing in the background. So essentially, any time in the context of this class that a web application is doing more than one thing, that means there's some sort of asynchronous programming that's kind of going on in the background. So in general, like outside of the context of this class, asynchronous programming is just when essentially two things are happening at once, either being coordinated with one another or not. So there's a little bit of a distinction that we'll draw between asynchronous programming and parallel programming as we move into this. So normal parallel programming, you have things just happening in sequence, whereas asynchronous programming is you need some coordination among those things, basically. So one of these kind of building blocks of asynchronous programming is the concept called a thread, which you might have heard about in other classes before. So the typical, just kind of normal programming model, the one that we think about most often probably as developers, is where we have an application that starts and statements of code are executed in a sequential manner or in a branching manner depending on what type of logic that you have in your code. But basically, a series of things are executed until those statements finish, and then the program is done. So this is our traditional non-asynchronous model of programming. So when we start to think about asynchronous programming, this is when we start to have multiple things happening. So we have an application that starts, and we might have multiple threads, which are basically multiple lines of computation that are happening in parallel here. So basically, by allowing kind of this code to run at the same time, this is what's going to enable asynchronous programming for us in this class. So probably kind of one of the most close parallels that you might have been exposed to from this is like the concept of multi-threading that exists in Java. So in Java, multi-threading allows you to do more than one thing at once. And practically this happens through some programming abstractions, but down at the hardware level, it's either code is running on multiple cores or threads of a CPU, or is being handled according to some operating system scheduler that is simulating some sense of parallelism in the way that it's assigning instructions. So one way that this can be used in Java is if you're building a Java program that has a user interface. Oftentimes there'll be a thread that controls that user interface, and then background threads that are actually doing some sort of processing task. But you can also set up threads for a number of different reasons. Say you just want to do some computation in parallel to take advantage of the multiple cores of a computer. So the way that this works is you have usually some sort of, if you're talking about a UI-based application like we are in this class, you have some sort of thread that is controlling what's going on with the user interface. So if you're building an old school like Java Swing application, this is handling drawing things to the screen, updating the user interface, things like this. Then in the background, somebody clicks on a button and you need to actually process some information. That's actually going to be handled by one of these threads. So you're going to have some processing that's going on in the background, doing that computation. It's going to send that result back to the main thread, and the main thread will actually display that on the UI screen. So this is more or less the kind of programming model we'll be thinking about for web applications as well, right? We have a UI. We want that UI to be interactive in some way. And to enable that interactivity, we're going to necessarily have to do some sort of computation in the background. So that's why we're talking about asynchronous programming. So the key thing here is that these different threads can share data with one another. So this is both an extremely powerful and an extremely dangerous abstraction for developers. And we'll talk about why this is. So here we have some Java code, some relatively straightforward Java code, right? We have a variable v that we've declared. We have some basically some function that we are calling thread 1 and some function that we're calling thread 2. And these are going to execute on different threads of a machine. So very simple. So here we are setting v equal to 4, and we're printing out v. And here we're setting v equal to 2. Now, the danger of having a multi-threaded program in Java is that you can have, basically, you don't have any kind of guarantee of execution order of things that are happening across threads. And this can create a situation that's commonly referred to as a data race. So in this case, we have a data race in these two code examples, and that is that the print line in thread 1 could see either 2 or 4, depending on the order of execution that we actually get here. So if we look at this, so one scenario that we could have is thread 1 could first write 4 to v, thread 2 could write 2 to v, and then we could read v and print it out. And this would give us 2. The other scenario we have is first 2 is written to v, then 4 is written to v, then we read it and it's printed out, and that could print out 4. So this is what's known as a data race, and this is something that you have to deal with as a developer. You have to put checks in place in if you're doing traditional kind of multi-threaded programming. But multi-threading in JavaScript is a little bit different than this. So the reason I brought this up is because JavaScript handles things a little bit differently, and I want to show you kind of one of the more traditional ways of doing it first. So here we have some asynchronous code that's written in JavaScript. So this is actually pretty straightforward code as well. So we have basically we're requiring a library that we're calling request, which is basically just a way to request a response from a web page. So we are requesting a response from google.com. And if basically if this is a success, then we basically log to the console, hey, we've heard back from Google. And then at the end here, we're saying, hey, made request. So request here is an asynchronous call. So we have two print statements here. Who can tell me what gets printed to the console first in this situation? Exactly. So if you're looking at this just from a sequential point of view, you might say, oh, it's going to first say, heard back from Google and then made a request. But instead, it's going to essentially send off this request to another thread, let it execute, And the program is going to continue to execute here. So we're going to print out first made request, and then once that, what we call a callback here, returns, that's when we're going to get the actual response from Google and print that to the console here. So here request is this asynchronous call. And this is one of the first things to kind of know about asynchronous programming here, is that when you have asynchronous code, so you make like an asynchronous request, whether that is fetching data from a web page, trying to fetch data from another server, something like this, the code will essentially continue to execute within that kind of main thread of your program. So this is kind of one of the first things to keep in mind. And one of the other things to keep in mind that we'll kind of get into over the next several slides is when you have multiple asynchronous requests that you're making, coordinating those in terms of when one finishes and the other one starts can start to become a little bit challenging. And this is where we'll start to use some of the built-in features in JavaScript to actually help to manage some of that complexity. So now that we've seen kind of our first just very simple example of asynchronous programming in JavaScript, let's take a look at the actual conceptual model for what's going on here. So as I said before, kind of similar to the like Java UI example I gave, so there's basically one thread that is kind of, you could think of this as like the master thread in JavaScript. That's called the event loop. So you could think of this as basically like a continuous like do-while loop that is just executing the code, the normal sequential code in your program. Then as this event loop comes across code that is asynchronous, so these basically calls to like an asynchronous library or something like that, then it's going to spawn these off into different threads. And there's particular semantics about how it processes these different events. But this is kind of the main concept that you should kind of keep in your head, is you have this one main loop that's kind of controlling everything in your program. And then as you want to make requests to fetch data or things like this, then this is happening in the background using different threads. The event loop here is kind of the main controller of everything. And all of this is handled by the JavaScript engine itself. So a lot of it kind of gives us this kind of nice abstraction, this nice concept. All of your code runs here. So let's take a slightly more detailed look at this, right? So we have our main event loop. And let's say we're making requests to different websites to fetch data, in order to compute some stuff or display like images from web pages or something like that. So first, we might make a request to google.com, and that will get put in thread 1. Then Facebook, and then maybe from gmu.edu. And these will each get put into basically what is a FIFO, first in, first out queue here. And this is what we refer to as the event queue. So any asynchronous call that you make essentially gets put in this queue and gets processed in the order that it's placed in the queue. So here, first it's going to try to get the response from google.com, and then it's going to say, all right, are there any listeners registered for this event? If there are, we're going to call that listener, and we'll talk about the kind of code semantics of this in just a little, but basically this is what it's going to then send back to the program itself. And after this listener is finished, we repeat with the next event. Again, this is going through the same thing, checking if there's any listeners registered, and if there are, it's going to send that data back to the main kind of event thread, and so on and so forth. So you can kind of see how this is working, right? So any asynchronous call that we make is being put onto this thread and being processed. So one of the defining features of JavaScript and of web applications in general is that they're event-driven, right? So if we have a React application, as we'll see later in the semester, you start up that application by running npm start from the command line, and some initial computation happens to draw the UI and to maybe set up some variables and things like that. But after that, the application kind of sits in this state of waiting. The event queue is kind of continuously looping through, just kind of waiting for some sort of asynchronous event to happen, or really any sort of event to happen. So when somebody clicks on a button that triggers a asynchronous event, then that's going to be sent off to the event queue itself. So this is kind of one thing to keep in mind. It's almost like we have this, while, we're waiting for messages until the application is destroyed, we're essentially going to process each, message, in this case, each asynchronous call, until, the application is killed or shut down or whatever. So this event loop is the thing that's going to be, responsible for processing all of this as we're, as the application is running. So in this case, that means we have these snippets of code that are going to be making asynchronous calls. So if you're not familiar with the kind of the terminology here, the way that, these are usually called like event handlers in some way, or, like listeners or callbacks. These are all kind of terms that are used to refer to this type of asynchronous code. So essentially, you need to be able to write these event handlers in such a way that things are handled, gracefully and correctly according to whatever the goals of your program are. And there's a couple implications of how JavaScript works and how the JavaScript engine works that you need to be aware of when writing a, quote unquote, good event handler. So the most important implication here is what is called the run to completion semantics of JavaScript. So this is essentially a very fancy way of saying that if you have multiple events that are going to be, basically, kind of pushed into the queue, the second event is never going to finish processing before the first event has finished processing. So it's basically that kind of first in, first out queue that I was talking about earlier. So there's both good news and bad news with this. So the good news is, unlike Java, where we can, have multiple threads that are finishing at any given time, and we have to have, explicit control over those things, we don't have to worry so much about, data races or things like that. Things are basically just happening one at a time with these different asynchronous callbacks. The bad news for this is that means that if you, let's say you try to have some asynchronous code that takes an hour to execute, that could be really bad because that means nothing else can essentially, no other processing can happen in the background while that is, while that kind of singular event is processing. So I think you can already start to see some of the implications for how we need to design our event handlers or our asynchronous calls in this place. So basically, if the main implication of this is if you have something that is going to be doing relatively expensive computation in some way, you should probably try to break that down into multiple parts so that other things can, other events can be happening, while that computation, different parts of that computation are running at given periods of time. A few other important properties of writing kind of good event handlers for asynchronous code. So remember, the events are going to be processed in the order they received, and events could arrive in an unexpected order, depending upon, where things are in the processing of your code versus, how many events have finished or, returned or things like this. So one thing you want to do with your event handlers is to check the current state of the app to make sure that that current state is more or less what they would expect, before they go and make that asynchronous call or, process data accordingly. So this is something that you probably won't run into too much in this class, but I want to cover it kind of just for completeness, related to some of the topics of asynchronous programming. So I talked about this event queue that the JavaScript engine is kind of maintaining. And the way that I talked about it so far, it seems that every type of event is treated equal, right? It just gets put on the queue and things get, processed in that, particular order. But that's not entirely the case. It's a little bit more complicated than that in the way that the JavaScript engine works. So basically, there are different types of events, different types of asynchronous events that you can essentially call in JavaScript. And the JavaScript engine does give priority to some events over other events, just for the sake of essentially optimization, for having the engine be very performant and run very quickly. So at the top, we have things like timers, IO callbacks, whereas things like polling or close callbacks are going to be more towards the bottom. So this isn't something that you're likely to it's likely to like affect your code that much, as you're writing it, because a lot of this is handled kind of transparently in the background in the JavaScript engine. But I have had a few students in the past with projects have really weird bugs that were actually traced back to, the ordering of events in the JavaScript engine. But it's usually in very exceptional cases. But if you want to know a little bit more about this, I have some resources kind of at the end of the page, at the end of the slide here. But again, probably something you won't need to go into too much detail on. All right, so we've talked about this general concept of how JavaScript handles this kind of like parallel and asynchronous programming. So there are some benefits versus the other type of model which Java uses, which we've already gone over, called explicit threading. And that is, writing your own threads can be really difficult because you have to constantly reason about what the state of the different threads are and what's being returned when and things like this. And if you look at studies of bugs in various types of applications, one of the top categories is often actually related to different asynchronous programming concepts because it's inherently difficult to reason about. So while kind of JavaScript's engine eliminates some of this in the way that it orders events, there are some downsides, right? You can't have super slow event handlers because that's going to kind of back up the queue and prevent things from being actually executed. And there can be certain situations where you do have data races, but because of this programming model, they're typically much easier to reason about. So I want to give an example of the run to completion semantics here just to kind of illustrate what's going on. So here, essentially what you need to know here is that any function that's handling an event and the functions that it transitively synchronously calls after that asynchronous event are going to keep executing until that function finishes. So basically, the high-level way of saying this is the JavaScript engine is not going to handle the next event until that event handler finishes. So let's say we have our event queue here, kind of on the left, and we have several different normal statements of non-asynchronous code that are essentially getting executed here. But then we have a couple asynchronous callbacks that exist as well. So essentially, if we have this first callback, it's going to call function f and then g and then h and then I. So basically, what we need to know here is that j is never going to execute until after I finishes. So even though we might have kind of multiple callbacks within this function, the next one is never going to process until the previous one has finished because of this run to completion semantics of JavaScript. So this is really nice because, again, it kind of avoids that problem of threads overwriting data in a way that was somewhat unexpected. And we'll see some examples of this, and we'll get some hands-on time with this a little bit later in class. So I think it's a little bit easier to understand once you're actually working with the code. So this is nice, but again, there's a couple implications here. So the first is, as we've said, and I'm kind of drilling in here, event handlers should never really block. You never really want to do expensive computation on them. Anything that's going to take a long time, you want to try to break into smaller pieces. So if we have this big implication that we need to break down these more expensive computations or this more expensive logic into smaller chunks, how do we go about actually doing this? So if you need to do something that takes a long time, it's best to split this into multiple events. So for example, let's say similar to homework 1, let's say you had a data set with 1 billion rows in it that you were processing. But you wanted to make sure that a user could continue interacting with some front end of your application as you're maybe calculating something from those billion rows. Let's say it takes maybe a minute to get through those billion rows. So in this case, we may want to divide that data set up into chunks, right? So maybe we have something that takes the first 100 rows and stores some incremental result for that, then gets the next 100 rows, stores some incremental result from that, and then at the end, it can give the user the full result. And one of the benefits of this is, let's say the user clicks some process button, they could continue to potentially interact with the application, or other types of processing could be happening in between these different calls to this long-running computation that we're making. So basically, by breaking it into these smaller chunks, we allow the flexibility of other stuff to happen in the application. That way the user's not just sitting there with a spinny wheel, making it seem like the application is really slow. So this is kind of one way that we can get around one of these major programming implications for asynchronous code in JavaScript. A couple of things to note here, though, is that if we are breaking down the computation like this, the application state could change. So maybe the user changes the request and only wants calculations on half the data set. So we would need to, after each asynchronous call that we make, kind of check the application state and make sure we're still actually doing what we intended to do in the first place, depending on whether something changed in the overall state. So this is one thing that you'll need to kind of check in these certain situations when you're going to be hopefully breaking down some of these longer computations. So we've kind of now reached this kind of overview of asynchronous programming. We've seen, we have an idea of what the JavaScript event queue is, what the event loop is that's going to actually be executing our code. Now we've seen an example of run to completion semantics. But as you start to kind of practically work with these kind of asynchronous concepts, one challenge is actually coordinating how these different asynchronous calls all mesh with one another. So the way that this is usually handled is that most asynchronous functions let you register a second callback that can be used in the case that maybe something doesn't go as planned, right? So let's say you make a request to google.com and God forbid Google is down for the millisecond that you try to access it. Then in that case, you could actually gracefully handle an error that may happen in that case. So this does happen. Servers can go down. There could be weird network stuff going on that prevents a message from being received. And this is an important property of these event handlers, is to check for cases when something goes wrong and handle those gracefully. Either maybe retry the request or provide some sort of helpful error message, something like this. So this is something else to to kind of think about as you're working through this type of programming. So as I just alluded to, we've seen the power and kind of some of the elegance of asynchronous programming in JavaScript, but how do we actually sequence events? How do we make sure that we have our non-asynchronous code that's just kind of running through the event queue, it's just processing things instruction by instruction, but then we have this asynchronous code. But what if we want to stop the computation of of our normal code and wait for something to return before we move on? How do we do that? Or if we have multiple asynchronous calls and we want to do some computation in between those, how do we coordinate this effectively? So here's where some of the JavaScript language features start to come into play. So we have a couple of goals with these language features. So the first is we want to be able to clearly distinguish what is synchronous code and what is asynchronous code, because this will help us reason about it in a way that's a lot more straightforward. Second, we want to enable some, some synchronous computation to occur only after some event has happened, without needing to go through like crazy nesting of code, and I'll show some examples later in class of this. We also want to introduce some ways to better handle errors, and maybe even potentially, have error handling to the point where maybe we either retry things or go down different, execution paths, things like this. And then finally, what if we have multiple asynchronous calls that we want to wait for before we, actually go on and do some sort of computation? So, let's say we broke something down in this long-running computation down into multiple things, but we can't compute the thing until we get everything. We need some way to be able to collect these multiple different asynchronous calls and wait for them to all finish before we proceed with actually computing something. So this is where our first kind of JavaScript language construct comes in. And this construct is something that's known as a promise, which is kind of I've always thought it was an interesting name for this, but it's an apt name, I think. So basically what promises are is they're a wrapper around any asynchronous call. So you make an asynchronous call, you can essentially wrap this in a promise, and it helps us to coordinate this asynchronous code. So essentially what promises do is they represent how we get a value, and you can then coordinate basically saying, all right, once this data that we've been promised is actually returned from the asynchronous call, then we want to do some pieces of computation. So the nice thing about promises is that they can organize a lot of these different steps that can need to happen in order to, have asynchronous code that makes sense. Oftentimes you want to coordinate different things to happen one after another, and promises can help us do that. And at any state, a promise is either unresolved. So for example, if we've made the asynchronous call and it's on the event queue waiting to be processed, it would be unresolved. It could succeed. So the asynchronous call is processed and that value has been sent back to the promise and we have access to that value. Or it could fail. And this would be in the case of like an error or something like that. We get a 404 or like a 500 server error or something like that. Then in that case, the promise could fail. And it explicitly tells us that. So we can actually handle those cases more gracefully. So let's take a look at a couple examples of how we can actually use promises here. So the way that this works is first you want to declare what you want to do when your promise is completed. And you can do this using the .then keyword. So here we have relatively simple asynchronous call, right? We are fetching data from the web page, https://github.com, and we're saying, okay, then we're defining this function that is getting basically the response from this asynchronous call. So whatever the response of this fetch call is from github.com, we're essentially taking that value as a parameter. And in this case, we're just returning the value of the text of what's returned by github.com. So this could be like the HTML of the web page, or depending on how GitHub is configured, potentially something else. And we can also add error handling code. So we can catch if there's certain types of errors and either log these to the console so that we can debug them later, or even introduce some code to alert the user that something went wrong, things like this. So basically adding this coordination with this .then is what's going to allow us to kind of wrangle the weird complexity that can happen when we're working with asynchronous code. Now, probably one of the most powerful things that you can do with promises is a concept that's known as promise chaining. So basically, you can promise one thing, and then another, and then another, and then another. So we can promise to get some data, then we can promise to get some data based on that data, and then we can promise to get some data based on that data, and you can basically have these kind of chained computations where you're just kind of continually waiting for certain values to get returned before you end up manipulating them. And if there's an error at any point during this, you can report the error and kind of handle it gracefully. So let's take a look at what this looks like in code. So here we have a custom defined promise, which I'll talk about in just a sec, that we're saying, okay, my promise.then. So this is, just think of this as basically some sort of asynchronous call that's happening here. And we're saying, all right, once this asynchronous call is happening, we're taking the result of that as a parameter into this function, and we're saying, all right, we're going to return whatever the result of this step is. And then we can chain another then statement here, and we can say, all right, once that is done, we can get that result, do something here. That could even be additionally asynchronous code, and then return that there, and so on and so forth. And this can allow us to kind of create these long-running chains of computation. And it can also help to break some of these bigger things down into little steps. And then at the end, we can have this catch function. And the important thing about this catch is that it's going to correspond to any of these promises. So if we get an error on the second one here, we're going to get it down here, and we can handle it all kind of in one place gracefully, depending on the type of error that we actually receive. So promises are kind of a built-in feature to JavaScript. So essentially, you can turn any sort of asynchronous call into a promise using the .then keyword. But you can also create custom-defined promises that could be useful if you want to customize how they're handling certain types of data. So the way that this works is, you can set a new identifier. So here we're setting this variable p equal to a new promise. And then you declare a function that has two parameters. One is resolve and one is reject. So essentially resolve is what happens if the asynchronous call actually completes successfully, and reject is if there's any sort of error. This is what you want to happen, basically. So this can be useful in certain situations where you want to really fine-grain control over what's happening with the asynchronous call and what type of data is being returned back, for example. But more often than not, I think you'll probably find yourself writing your own promises very seldom in this course. You're probably not going to do this super often. But just as an example of this, let's say we want to define a promise for loading a given image here. So here we can say, all right, we have this new promise with these two parameters, and if we want it to resolve, basically we will resolve this image that we get. If we want to reject it, then we would essentially print out the error message that's passed through the actual asynchronous call itself. So pretty straightforward. You probably won't find yourself doing this often, because you can typically just use the kind of default data that's returned by some given asynchronous call just at face value. But this is a tool that you can have that can make certain types of, maybe if you're dealing with a really complex asynchronous API and you only want to return like a portion of the data that it returns, this could be something that could be useful for you. So again, this is just pretty much the basic syntax here. The main thing that you want to know is that you can do some sort of computation basically before you are essentially resolving that promise or resolving that asynchronous call. And again, you can be selective about what types of data you want to return or things like this. So let's take a look at kind of like promises in action here. So later on in this course, we're going to be talking about how to store data for web applications, and one of the ways that we're going to do this is through a real-time database provided by Google called Firebase. So you can just think of Firebase here as a database. So essentially what we're going to do here is we're going to get some value from that database, and then we're going to push a new value to that database, and then we're going to print out OK. So here we have, basically this is a reference to this database object that we've defined up at code that's not shown here. And we're saying, all right, we're going to get some value that's stored in this database. And then once we get that value, because remember, this is a database that's stored on some server, we don't know, that's an asynchronous call we're making to get that value. Once that value is returned, we're going to get the text related to that part of the database we're trying to return. And that's going to then go into the next part here. Once we have that text, then we're going to say, all right, we want to modify this text, because we want to take what's already there in the database and we want to add the word seriously before it. And then once we've done this, this gets pushed. This is another asynchronous call since it's getting pushed to the database. And then after that's happened, then we can print out OK, because we know that each of these steps has actually functioned kind of step by step here. And of course, let's say we had an error accessing the database or something like that. We could add some error handling code down at the bottom in case something goes wrong. So this is basically how you would typically use promises within your web application. So any questions on this before we move forward? And we'll get an example, or we'll get an opportunity later in class today to actually get hands-on with some of this stuff so you can see how it's working. OK. If you do have questions as I'm going along, please feel free to stop me. So as I was saying do this, then do this, then do this, exactly as we showed earlier. And if you ever have an error, do this. OK, so we talked a little bit about how to test our web applications in the last class using the Jest framework. So I want to briefly touch on how you test things that are asynchronous in nature, because there's some weird stuff that can happen since it's not just normal synchronous code that you're used to dealing with. So here we have this function that is get username, and we pass it some user ID. And this is essentially making some asynchronous call that's essentially trying to get this username. And let's say we want to write a test to see whether or not the fifth user here is equal to Mark. So seems reasonable, right? We just expect that to work as normal. But there's a couple of different ways that we can actually write this, and there's some important differences between these. So this one would actually, even if this was actually true, this assertion statement was true, Mark is in the fifth position, or index 4 in this case, this would fail because of the way that asynchronous calls work. If you were to just kind of set this up and try to run this, this call would not have returned by the time the test actually goes to evaluate this expect value. So it would try to expect this, and it would basically get a promise object instead of the actual value itself. So you can't just directly test the asynchronous code this way. You need to be a little bit more careful about it. So we can do this using these kind of bottom two sequences here. So here we can say, all right, we're going to expect this given assertion that we have below, and we're only going to essentially expect this using this kind of asynchronous syntax that we've been talking about so far. So let's kind of step through this. So here we have our asynchronous call here. So we're saying, all right, get the username at position 4 here. And then we're going to use a promise that's going to say, all right, once we get the value of this, we want to then take data and expect that the data is going to be equal to Mark. So essentially here, we're essentially making sure that this asynchronous call completes before we actually go and have the assertion statement or the expect statement here that's going to actually check the value. And down here is basically just a shorthand way of writing the same thing, where we can say resolves.toEqual. So this is basically encapsulating this arrow function where we don't have to explicitly do the dot then. We have this kind of shorthand way of doing it that's just resolve. So the bottom two here are basically functionally equivalent. So this is one thing to keep in mind when we're actually testing asynchronous code in JavaScript. And when you're working on homework assignment 2, this may be something that you run into. So in homework assignment 2, the basic idea is you're going to be creating a server that is going to have some API endpoints that somebody can access, and it's going to compute something once those API endpoints are accessed. Now, if you go to test these things, let's say you're loading in a data set from some remote location. If you don't give the tests enough time to load in that remote data set, you can actually run into issues. And I'll cover this in the homework instructions, but this is an example of actually where you might need to kind of use some of this in practice. As I mentioned at the beginning of class, we're going to be introducing some of the kind of concepts behind asynchronous programming in the first half of class, and looking more at some code examples, as well as one additional really important language feature that we can use to help coordinate our asynchronous code in the second half of class. And it's exactly what we're going to be doing now. So as we've already seen, synchronous code is basically, when you make a function call, the function call returns and the work is done. But for asynchronous code, when you make a function call, the function returns immediately before that work is actually complete. And then the execution of the code continues on your normal synchronous code. So we need a way to basically start to wrangle this complexity, to order things in a way that actually makes sense. So the way that a lot of this is handled in JavaScript is that like as I said before, the JavaScript engine is kind of the thing that's managing a lot of this kind of in the background from us. So the JavaScript engine is going to be different depending on where it's being run. So if it's running in a browser, or if it's running in Node.js, this is what is going to be the mechanism, the engine that's handling a lot of these different asynchronous calls for us. And it's just important to have an awareness of this, as we're going through and doing this type of programming. We talked about the run to completion semantics. So remember, if we have a function that is handling some sort of asynchronous event, and if we have functions that are essentially being called or that are that function is calling, we're going to basically complete the execution of any functions that function is calling before we go to the next callback, or before we go to the next asynchronous part of code that is actually happening here. And this will become apparent over the next set of slides here. But basically, in short here, J is never going to execute until after I finishes in this example. So as we said, we want to make sure that these event handlers never block, because that means, if they're doing, by block here, I mean doing some sort of long-running computation, because that means we're going to not be able to do other work on this kind of event queue that JavaScript has. We talked about promises and how you could chain different promises together, so we can, basically coordinate things on a step-by-step level when we have different asynchronous calls, which is a very, kind of useful way of actually coordinating things. And we can catch errors at the end. So now what I want to talk about in this lecture is I want to give a few examples, kind of stepping through how we can work with parallelism and, asynchronous code in JavaScript, and kind of explain that those are two different things. Then I'm going to introduce the async and await features of the JavaScript language. You can think of this as basically similar to promises, and they can be used in conjunction with promises, but they make it a lot easier to reason about asynchronous code. And we'll talk about why that actually is as we step through the examples. And then we'll have a programming activity that, if this is your first time really working with asynchronous JavaScript, I highly encourage you to stick around and work through this. And I'll be more than happy to go around and answer questions. And usually there's quite a few questions as we're going through this activity, since it's a very new paradigm for a lot of people to work in for the first time. But first, let's take a look at some things that we can do in terms of coordinating these asynchronous calls in different ways. So we talked about how you can coordinate asynchronous calls step by step using promises. But remember, one of the things that we said we wanted, in being able to manage these asynchronous calls, was being able to wait for a lot of things to finish all at once. So promises actually do give us this ability. So let's say we wanted to, fetch a bunch of images and then display them all at once, on a UI for some reason. So we could do this using the promise mechanism. So we could say, all right, we're going to use this promise.all keyword that we have here, and we're going to say we have these two images, and we're going to make these two asynchronous calls to these load images. And we're going to say, okay, after, in this case, both of these or all of these images, we get the results of them, then we're going to actually append these to the actual HTML of our web page and display these to the screen. And if there's any error, then we're going to log out some sort of helpful error message. So this can be useful, again, when we want to wait for several different asynchronous calls to return at once before moving on and doing some sort of computation. So actually, in the in-class example today, we'll see one popular way of using this is to actually put a bunch of asynchronous calls into like a list or a queue, and then we can essentially send all of those calls out to the JavaScript event handler and wait for them all to finish. So here we just have like a list we've defined ourselves, but we can make this arbitrarily long. And we'll take a look at that during the programming activity today. So now I want to go through a kind of high-level example where we step through the different kind of language features that we've seen for asynchronous programming so far. And we're going to do this first just using normal asynchronous nested calls. Then we're going to use promises. And then I'm going to introduce async and await. And we're going to see how it works with async and await, which is a little bit different. So this example is going to be fairly simple on the surface, right? So we are going to have basically a bunch of data that we need to fetch, a bunch of different items. Then we are going to need to combine these items or group them together. So for example, let's say these are like different APIs. Maybe it's some news updates and some calendar updates. So we need to group them by their type. And then we need to update that information on the display. And then I will explain the example after each of these different cases. So let's take a look at how this would work if we were just writing this with no asynchronous code at all, just normal synchronous JavaScript code that we know and love. So the way this would work conceptually is we get an item, get another item, get another item, get another item, so on and so forth, until we get all of the items. And then we need to first group all of the calendar updates, then group all of the news updates, then we can update the display, and I can explain this, which in this case is pretty straightforward. So as we can see, it's exactly like we'd expect, right? Each thing is happening one after another in the synchronous code. Now let's take a look at what this looks like for an asynchronous version of this. So for the asynchronous version, we're first going to make an asynchronous call that is going to get all of the items. So maybe we have an asynchronous call for each one, we group them together, so on and so forth. Then we're going to make an asynchronous call to group them together. Then we're going to update the display. And I'll go into how this works within the code on the next screen. So let's take a look at what actually happens in some of these different cases. So this is going to be a running example we use, and this is also going to be the example that we use in today's programming activity. So I'm going to take a little bit of time here just to explain what's going on step by step. So at the top, we have this magical library that we're importing as lib. So essentially, you can just think of this magical library as being able to fetch things, group things, so on and so forth. You don't need to know the contents of it. It's not really important. Just trust that it actually does what it says it does. So by using the things in this library, we're going to first here, we're going to say, all right, we have a list of things to fetch. So basically, we define this list. And you'll notice there's two types of things, right? Or actually three types of things. We have T, S, and M. And there's different numbers for each of those things. The letter is going to indicate essentially the type of the item in this case. Then we're defining an empty array that we're calling stuff. And then here we have a for loop. And basically, this for loop is basically just essentially looping through this list of things to fetch. And we're pushing each thing that we get to the stuff array. Now, this seems a little redundant, but this will become clear why we're doing this later on. And then every time we do this, we're going to print to the console, got a thing. So then at this point, we have basically just put the contents of things to fetch into the contents of stuff. Pretty straightforward. Then once we have this, we're going to then group the stuff. So we have three different groups we need to do. So we're going to say, all right, I want to first group this stuff according to T, group this stuff according to M, and group this stuff according to S. And then after each one of these is finished, we're going to print out grouped. And then finally, at the very end, we're going to print out done. So we'll see variations of this example using different types of these programming paradigms we've been talking about to see what actually happens here. So let's actually go and run this code to see what happens here. So it's going to print out got a thing, got a thing, got a thing. Remember, it's basically just looping through this for loop, printing this out. This is the synchronous version. We're not doing any asynchronous stuff here. Once it gets all the things, it's going to group them together. And then at the end, it's going to print out done. So any questions on this example before I move forward? Hopefully it's pretty straightforward at this point. This is just our basic kind of base level synchronous example. Now, let's take a look at an asynchronous example. So in this asynchronous example, we're not using promises in any way. We're essentially just nesting the callbacks, basically nesting each asynchronous call so that we can control when they are actually happening. So if you see this, you start to understand why we need promises, because this can get really crazy if we want to do asynchronous programming in a manner like this. So in this case, we are using asynchronous programming, but there's no parallelism here. So there's nothing that's happening kind of simultaneously. So because we're just nesting things, one after another here, this behavior is going to be effectively the same as the last example that we just saw. So, OK, here we go. So we can see the output of this. It's going to be exactly the same as the previous example, right? It's going to essentially get each thing in parallel, even though these are asynchronous calls. But because they're all nested with one another, and JavaScript has run to completion semantics, it's just going to happen essentially one after another. And this kind of continues on. So this is actually a way that we can use asynchronous programming, and we can coordinate things in an effective way, right? Like this did what we wanted to do. Like we got all the things before they were grouped, before we printed out the end message, but it's not any faster. It just kind of works exactly the same way as the code we had before, but now it's impossible to read. So let's take a look at how we can actually do this using some of the kind of callbacks that we've talked about so far. So let's go through this example again. So we have the same array. We've got our empty stuff array. In this case, we're defining 3 other things that we're going to be using basically as the groups for the different elements here. And we're going to set this variable that's going to essentially be equal to the number of things left that we have to fetch from this initial array. And we're going to have a for loop here. And again, we have this magical lib. And here we have this kind of lib.getAsync. So basically we're fetching, you can think of it as like data for each of these different things. And as we're fetching these, we're pushing these to the stuff array. And we're printing out, OK, got a thing after each time that we get this. But remember, because this is an asynchronous call here, we are basically returning immediately after each of these. So we're starting to introduce some parallelism here. So because we're not using promises here, we have to keep careful track of the state of the program to know like how many more times we need to do this. So here we're saying, all right, we're basically decrementing the amount of stuff we need to get after each call that we're making. And once that's 0, then we can start grouping stuff together. So then we can make these calls to these asynchronous functions that are going to group things together. And we can do this again until we've kind of exhausted the array. And we can do this for each of the 3 groups before we finally print out done down at the bottom. So let's take a look at what this code looks like when we run it. Quite a bit different here, right? Because as I said before, we are essentially just running this code, very, very quickly. We're essentially putting each of these different things onto the event queue. The event queue is processing it very quickly, and then it is, all returning, together. So this is being processed by the different threads in the event queue, and then we essentially do the same thing with the grouping. But again, we have to do all this coordination among like checking to see where we are and how many things are actually happening before we move on to the next thing. It'd be much easier if we could coordinate this a little bit better. And we can do this with promises. So here we have another example where we are using promises, but we have no parallelism. So this is basically just happening asynchronously. So again, it's similar to the nested idea that we had before, but instead we just have .then, 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 because we're just doing each thing one at a time. We're not using promise.all here, right? We're just essentially executing each thing as it actually happens. So if we were to run this code, we would get a similar output to what we saw before, where it's going to execute in a way that behaves like synchronous code. So basically we're doing things right here. Like this code is executing correctly, but we don't have any parallelism in it. That is, we are not putting like multiple events on the event queue at once and then waiting for all those to process, from the event queue. But we can introduce this parallelism by using this promise.all notation that we just introduced a few minutes ago. So in this case, it's exactly the same setup as before, but rather doing a promise.then for every single asynchronous event that we're trying to do, we only have one .then. And that's in between basically getting getting all the things, so fetching all the things from the server, and then grouping all the things. So all we're coordinating here is we're saying, OK, wait until we get all of the things through this promise.all, and then group all of the things together. So this is functionally equivalent to this code that we saw earlier, where we did the asynchronous coordination, where we had the parallelism. But if we look at this, this is far easier to read and understand. At least it should be. We're not having to keep track of where we are in the queue. We're not having to manage the state of the application in any way. We're essentially just saying, all right, we're going to promise.all, basically this array of promises that we've created. So let me actually step through this because syntax might be a little bit strange. So we have the normal kind of setup we have at the top. We have the things to fetch. We have our empty stuff array, and we have our variables for the groups. Then we have this empty promises array that we've created or initialized as well. So essentially what we're doing here is we're looping through each of the things to get here, and we're essentially calling each of these different, we're essentially creating a list of asynchronous functions that we're going to call. So by doing this, we're essentially saying, all right, we're taking this promises array. We're saying, OK, push our lib.getPromise of whatever the current thing to get is, and put it in this promise array. Then once we have this array of promises, this kind of, you could think of this as like an array of functions, asynchronous functions, we're going to say promise.all, this entire array of functions that we had. So basically, you could think of this as like async get t1, async get t2, async get t3, all just in this array of promises. And then once we get all of this data, we're going to store that data into our stuff array, and then we're going to essentially go through and do the actual grouping at the end. So we're going to say, all right, once we've gotten this data, we're going to say again, promise.all, and we're going to say, all right, we're going to do our asynchronous grouping for each of these things. And then finally, at the very end, we're going to store those into variables and then print out that we're done. So again, this is kind of functionally equivalent here. So if we look at what this is actually like to run, it'll be the same behavior to what we saw before. So rather than just printing out all the stuff, each individual thing, we're just saying, all right, we got all the things, got all the groups, and then we print out done. And basically this little promise array that you have up here is when we say, all right, we've got this kind of set of promises that are currently pending. So this is one way that we can see that we can kind of coordinate using asynchronous calls in JavaScript, using this promise.all, where we can both kind of order the asynchronous calls in a way that makes sense, and we can have parallelism by using that promise.all. If we were just to use the kind of promise.then, again, we wouldn't achieve that parallelism, but because we have the promises.all, we do achieve that here. So hopefully that kind of shows you why promises are a little bit better than having to do like all of this bookkeeping and kind of extra complexity and stuff in code that you might have. But as I finish telling you how great promises are, there are still a few issues that we need to deal with. And this is where the async and await keywords actually come into play. So the first issue with promises is basically in how it does like error handling. If you have nested promises, error handling can become challenging. But beyond that, it can be difficult once you have a lot of promise chaining and parallelism where you're promising multiple things. It can still become difficult to reason about. So as people have begun to work more and more with asynchronous programming in JavaScript, the async and await kind of keywords or language features have been introduced. So this is basically the kind of like latest and greatest way to work with asynchronous functions in JavaScript. And you can think of this as, the high-level description is, it's a way to make your asynchronous code look more like synchronous code so that it's easier for you to reason about as a developer. So basically, the key idea here with this async and await is basically you can declare any function to be an asynchronous function. And then you can essentially await for something to happen before proceeding. And we'll see some actual examples of this here in just a sec. So this is basically what this looks like, right? We have this function that we've declared that is just returning hello. There's nothing asynchronous about this, right? Like it's just a normal piece of code that's not like an asynchronous API call, but we can declare it as async by using this keyword. And then when we call this hello function, it's going to behave like an asynchronous function. So this automatically returns the return type of the function into a promise. Now in this case, it wouldn't really matter because this would return almost immediately, but this is the general idea. So let's take a look at an actual example here to see how this works in practice. So here we have this function that is basically set to resolve after 2 seconds. So we're saying, all right, we're going to return a new promise that's going to resolve basically this timeout. So essentially this is going to return after 2 seconds have passed. That's all the top code is saying here. And then we have this function down at the bottom that we've declared async with the async keyword. And we're saying, all right, this is a function that's an asynchronous call. So we're going to log to the console that we're calling this function. And then the result of this is that we're going to await this other asynchronous code that we have up here, this resolve after 2 seconds, and then we're going to log the result. So basically what this means is like this top function here is essentially standing in for like some API that you might be using from like, some online service or something like that. So let's say, this resolve after 2 seconds was like an API that was provided to us from Google. And we're writing this function down here below, but we want to coordinate this asynchronous call that we're making within this function. So essentially we're just going to say, all right, because we know we want to make an asynchronous call within this function, we're going to declare our kind of parent function here as async. And then we can say, all right, we're not going to execute any instructions after this await keyword until this API value has returned, until we get the value here. So in this case, there's no value. It's just like waiting 2 seconds. But that's the general idea here. So if we go ahead and run this, going to see it's going to say calling, and then it's going to say, resolved after that. And we're going to kind of print the result of that. So the reason that this works the way it does is because of this async keyword here. So let's take a look at our kind of running example that we've been seeing so far. So we're going to shift from using promises to using async and await here. So again, I'm going to start with basically the non-parallel way of doing it, right? So this is essentially the way that you do this if you wanted it to behave in a synchronous manner. But as we can already see, the code's a lot cleaner here at this point already, even for this kind of synchronous version of it. So the way this works is we have this async function that is get and group stuff because we're going to be making some asynchronous calls within it. We have our things to fetch, we have our stuff array, we have our different group variables, and we go through the same thing that we did with the promises, right? We're basically pushing each thing that we need to get, each kind of function call to this in this promise array. And but here, because we have the await keyword here, we're essentially saying, all right, hey, don't move on until we've gotten each of these things. So basically it's going to say, all right, we're going to call this function, it's going to wait for that function to call, and then we're going to say got a thing. So you can kind of see this is already going to behave synchronously because we're awaiting every single iteration through the for loop. Then down below, we have a similar type of thing here where we're saying, okay, await this asynchronous group, await this asynchronous group, and await this asynchronous group. And if we're to actually run this code, it would run much in the same way we'd expect the other synchronous code to run, where it's just sequentially, got a thing, got a thing, got a thing, so on and so forth until it gets everything, groups everything, and then it's at the end. One thing to note here is that we do have this call to this function down at the bottom here. So we're defining this asynchronous function, but we actually need to call it down at the bottom for this actually to work in practice. So this is the synchronous version of this. But the in-class activity is actually going to be for you to implement the parallel version of this. We're going to use async and await to make this behave not in a synchronous fashion, but in a parallel fashion, where things are actually happening kind of more efficiently in the background using the JavaScript event queue. But before I turn you loose on that, a couple just kind of reminders for async and await as you're working on this example. So the first one is that you can only use the await keyword from a function that you've declared to be asynchronous. So basically this is indicating to the JavaScript engine, hey, this function might actually make some asynchronous calls, so we need to be looking for that await keyword. And you can only await on functions that return a promise. So for the purposes of this in-class example, you can think of any of those library calls to that magic library I talked about to return a promise, any of those asynchronous calls. But typically this will be like an API or something you're trying to access from some other server or some other service, something like this. And remember, the await keyword makes your code synchronous. So if you're going to be trying to turn in the example that we just had into something that is parallel and not behaving synchronously in nature, I'll give you your first hint. You're probably going to need to await a promise of multiple things, because you're going to need to basically send off multiple things to be processed by the JavaScript event queue before you process them kind of all returning at the same time. So this is exactly what the in-class activity will be for today. So I have the Replit repo on the slides. I'll post this on Ed in just a minute. So I encourage you, particularly if you are kind of new to asynchronous programming in JavaScript, feel free to stick around and work on this. You can work in groups or pairs. It doesn't matter. There's nothing to turn in for this. This is simply for your practice to kind of start to wrap your head around this idea of asynchronous programming. But with that, I'll post this to Ed right now, and I'll be more than happy if you have any questions as I'm walking around, or if you want to get my attention, feel free to just raise your hand.